Okay, so today is our last day of lecture material. So we will be stopping to review and test and then have a couple days of exam review prior to our final exam coming up. So I'm going to spend this one day in chapter 10 on correlation and regression. A lot of you have done correlation and regression in high school math classes. So this is not going to be a lot of new material, but it is something I want to at least address briefly and maybe throw in a few additional details that you haven't seen before with this. So I'd like to, like I said, briefly look at section 10.1 on correlation and 10.2 on regression, and that's going to be all we have time to cover in this course. So a correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. So we want to look and see sometimes is there a correlation between these two, like maybe the amount of time spent studying and the grade you make on a test would be an example of something we want to see if there's an association between those and how strong is that association. So the way that we're going to be analyzing that is through a couple different methods. The first one is going to be with the scatter plot. So the scatter plot is a type of graph and it looks at paired data. So we're going to look at pairs of data with X's and Y's. So it graphs these. This is also called your scatter diagram, scatter plot. Basically, your horizontal axis is used for the X variable. The vertical axis is used for the Y variable. And you've dealt with scatter plots a lot, so this is not a new type graph for you. So this is something that you might see as a scatter plot. This particular one is showing the correlation between waist circumference and arm circumference. So if we look at this, we're looking for patterns within these points. So here, the correlation is the distinct pattern of the plotted points. So if it does kind of line up in a line, and by a line, it's not going to be like a straight line. It's going to be more I've heard it referred to as more cigar shaped. If you could draw a circle around it and it looks kind of like a cigar, then that's going to be an indication that it's linear in nature. If you see points that are all scattered around with no real pattern to them, then those are not going to have a correlation between those. This particular one is showing weight and pulse rate, so it appears based on this graph that there is no correlation between the two of those. Sometimes it will form a distinct line that has a positive slope. So if it has a positive slope, then we're going to say it has a positive linear correlation between those. And basically that means as one increases, as the X is increasing, the Y is also increasing. So whatever quantities you're measuring for that, as one increases, the other one increases when you have a positive correlation. If you have a negative correlation, you're going to have a line that it's going to line up in a line that has a negative slope. And that basically says if you have a negative correlation that as X increases, Y is decreasing. So sometimes the more you have of something, the less it's going to cause you to have of the other thing. So looking at this is an R value, and we're going to start talking in a minute about the R values. But this R value is close to -1, which basically means it is a strong correlation. If you notice here, this one is not, we're going to basically be looking at the absolute value of these. So if I look at the absolute value of this one compared to this one, that absolute value is closer to 1 here. So you can see this is a tighter line, whereas here this is a little bit more spread out. Okay, if you have one like this that has no distinct pattern, then you're going to see an R value that's actually close to 0. So the closer the absolute value of the R is, the closer it is to 0, then that's going to indicate that there's no correlation. The closer it is to 1, then that's going to be a stronger correlation. Okay, so this one is, it is possible to have what's called nonlinear relationships. This would be a quadratic relationship. We're really only going to focus in this section on linear relationships. So we're not going to be working with any that have a quadratic regression or quadratic correlation. So this R is called your linear correlation coefficient, and it, like we mentioned, measures the strength of the linear correlation between the paired quantitative X values and Y values in a sample So it's an indication of how much they are correlated between the two, the strength of that correlation. So here's a few that we've kind of already talked about, and you can kind of see, again, the closer it is to 1, or the absolute value, again, is what we're looking at. Closer the absolute value is to 1, the more it forms a perfectly straight line. The more it gets away from 1, the more it spreads out. And then, of course, we have these that aren't even linear. Okay, so this just kind of summarizes it. If R is close to -1 or to 1, then there does appear to be a correlation, a linear correlation. If R is close to 0, then there does not appear to be a linear correlation. So close is kind of a relative term, and that's why we're going to also look at p-values to kind of make a decision about whether we can say that it has a linear correlation or not. One thing to keep in mind is that the R is a measure of the linear relationship, so it's not designed to measure the strength of a relationship that's not linear. And R is also very sensitive to outliers, so you really don't want to have outliers in your data set that you're trying to analyze. Okay, here is an example comparing shoe print length to height. So this would go in for like your L1, and this is going to go in for your L2, and you would come up with your scatter plot. Just as a reminder, you can go to your scatter plot by going to, if you go to second, y equals, it's going to bring up your stat plot menu, and it's actually graph number 1 that you're going to choose, and you're going to want to always end this with zoom number 9, and that's going to frame it around the data that you have put in. Okay, so when we look at something like this, it's not totally linear. These 4 kind of line up. This one's a little bit off to the side here, but we're going to go ahead and proceed with it and just take a look at what the R looks like, what the R is. But I wanted you to see what the scatter plot looked like for this data set. Okay, if you go to linreg t-test, and I'll show you in a little bit how to get to that, but if you go to this linreg t-test, it's going to show you your R value here. So when we have an R value of 0.591, that's not really close to 1 or close to 0, but it's kind of in that gray area where we're not really sure whether there is a linear correlation or not. So that's where we start to look at the p-value. So if there really is no linear correlation between the two variables, the p-value is the probability of getting a paired sample data with a linear correlation coefficient R that is at least as extreme as the one obtained from the paired sample data. So basically, you're looking to see how likely is it to get an R value if just by chance that is the value you got there. So that's kind of what you're looking for. But as far as how we're going to use that p-value, if we were to set this up and do a formal hypothesis test, and you really don't have to do this in this way, but you would set up a null and alternative hypothesis that would use the Greek symbol rho, and you would say that rho equals 0 and rho is not equal to 0. So basically, our null hypothesis is that we have no correlation exists. Our alternative then would be that we do have a correlation that exists. And these are the only 2 null and alternative hypotheses that you're going to use in this section. You're not going to be adapting these at all. It's going to stay the same. The null is no correlation. The alternative is that there is a linear correlation. Okay, so as far as how we go through and do this, if we look at that data set we're using there, you want to enter your data in for L1, and then to do your scatter plot, we're going to go to your plot, make sure it's turned on, and choose the first graph. And then, like I said, always remember to do zoom number 9, which is zoom stat. We'll get our graph here to look at. So as far as going to that linreg t-test, we're going to go to stat, go over to our test menu where we have all these other tests we've been using, go all the way down to letter F where it says linreg t-test, and that's the one that you're going to choose to use in this section. Be sure you tell it where your data is, L1 and L2, and then you want to set it on the does not equal here, and you're really not going to be changing that, so just leave it set here. And then press enter, and it's going to give you a listing that looks like this. You may have to scroll down with your arrow to see all of it, but your R is listed here. And we also have our p-value that's listed here. Okay, so our p-value is pretty large. You remember that normally we're going to compare this to some significance level, and typically our significance level is 0.05. So if our p-value is 0.296 and our alpha is, or significance level is 0.05, our p-value is larger than that. So what we're going to do is we're going to fail to reject the null hypothesis. So if you recall, what we had said was that our null hypothesis is there is no correlation. So if we're failing to reject that, then what we're going to do is we're going to have to still believe that there is no correlation with that. Okay, so just to kind of summarize that, a p-value of 0.294 is high, so it shows that there's a high chance of getting a linear correlation coefficient of 0.591, which is what we got by chance, when there is in fact no linear correlation between the two variables. So it's actually fairly likely to get this correlation value when there is no linear correlation at present there. Okay, so only a small p-value, such as those less than 0.05 or whatever your significance level is, are going to suggest that the results are suggest that the sample results are not likely to occur by chance when there is no linear correlation. So a small p-value supports the conclusion that there is a linear correlation. So when you get really small p-values, that is going to be saying that you do have a linear correlation. Okay, so if your p-value is less than or equal to your alpha, it's going to support the claim of a linear correlation. If your p-value is greater than your alpha, it does not support the claim of a linear. Okay, here's another example. This one actually is also shoe print length and height, but the Pearson correlation, that's another word for your R. So your R is going to be 0.813. Your p-value is 0.000 as far as our results on this particular data set. So because of this, we have an R that is pretty high, and we have a p-value that's definitely less than any alpha that we would be using. So this one, we would actually be able to say that there is a correlation here. And if you look at this, it does look like it lines up more in a straight line. Okay, so once we've established that there is a correlation, what we can do is come up with, is look at regression. So regression line, or the line of best fit, or the least squares line, is basically a line that is going to go through your points and serve as a prediction line. So it's going to allow us to predict values from that. So this is your regression equation. There's some pretty elaborate formulas for coming up with the b sub 0 and the b sub 1. But we're not going to, because of time, go into all that. We're just going to let the calculator do all of this for us. So this is kind of a visual showing the line of best fit. It's just an approximation of going through these points. Okay, so if I were to calculate this, then what I would see is that I'm going to substitute in for this. I'm going to have a plus bx, or it's going to depend on how you set it up. Your calculator uses an a and a b. StatDisk here uses the b sub 0 or the b naught and the b sub 1. Okay, so here's another one for us to find the correlation. So I'm going to let you put that in your calculator and find your correlation coefficient, which is your R. Okay, once you've put that in and you do the ln-reg t-test, you're going to see that your R is 0.795. So that would be a fairly high R value, and probably would be a linear, would have a linear correlation. So I want to go through kind of a summary of all of this. I know we went through a lot of that quickly, so I want to just kind of show you what I'm talking about with these and what I'm expecting you to be able to do. So this particular one, listed below are the numbers of chirps in 1 minute and the corresponding temperature in degrees Fahrenheit. And so we're looking to see, is there sufficient evidence to conclude that there is a linear correlation between the number of chirps in 1 minute and the temperature. So I've broken it down into several different questions here. The first one I want you to do is to construct a scatter plot. So if you feel like you can handle these questions, then go ahead and pause the video and try it. If not, then just kind of go with me as I go through this one. So to construct our scatter plot, we're going to put this in for L1, and we're going to put this in for L2. Okay. So we'll enter this data here for L1 and for L2. We'll turn our plot on, choose the first graph, and make sure we have it set up. And so then we see a graph that looks like this. So it does look like there is a linear correlation there with a positive R value. Okay, so it has a positive slope, so a positive R value there. Okay, the next one, we want to find the value of the linear correlation coefficient R. We're going to do that by going to our LinReg t-test menu. So we're going to go to Stat, and then go over to Test, go down to letter F, set it up with L1, L2, and the does not equal, and then press Calculate, and it brings up our screen here. So our R is all the way down at the bottom. So this is our R value. So that's going to be our answer to B. So we'll do 0.874. Okay, find the p-value. The p-value is up here at the top. So my p-value is 0.0045. So if we want to determine whether there is sufficient evidence to support a claim of linear correlation, this would be less than our 0.05, which is our significance level. So we're going to reject the null hypothesis. And if you remember, our null hypothesis was that there is no correlation, and the alternative is that there is a correlation. So by rejecting the null hypothesis, we're able to support and say that there is a correlation between these. Okay, so find the regression equation. As far as finding the regression equation, we've got this model set out here. So all we really need to do is to substitute in the A and the B that they give us down here. So here's our A and here's our B. So I'm going to have y equals 27.52 plus B is 0.524x. So this is going to be my answer to part E. That's going to be my regression equation. Part F says find the predicted temperature at a time when a cricket chirps 1,000 times in a minute. Okay, so this is telling me how many times the cricket chirps. So I want to go back and look and see if that is my independent or dependent variable. So my chirps is my independent variable, which means that's going to act like my X. And the dependent one is going to be the Y, and that's going to be my temperature. So if I'm looking at 1,000 chirps in a minute, that's going to go in for my X. So I'm going to have Y equals 27.52 plus 0.524 times 1,000. I just noticed I left off a 0. Okay, so when I plug that in and evaluate it, I get 79.92. So basically, if the cricket is chirping 1,000 times in a minute, then based on our model, we could predict it to be about 80 degrees outside. Okay, for G, we want to find the predicted temperature when a cricket chirps 3,000 times per minute. So we're going to do the same thing here, and we're going to get 184.72 degrees. Okay, so our question in part H, what's wrong with the answer from G? Well, F was fine to use as a predictor because if we look back at our data set, the X's were all in the like 800, 900, 1,000, 1,100, 1,200, around in there. So 1,000 would be right in line with the data that our model was built around. But 3,000 is not anywhere close to these data values that it was built around. So when we go to plug in something that's way far away from what we use to create our model, then our regression equation may not be as accurate. So looking at this, it really doesn't make sense because if a cricket is chirping 3,000 times in a minute, then he's predicting based on our model that it's 185 degrees outside. So there's a lot wrong with that because probably the cricket's going to be dead if it's 185 degrees outside. So he's probably not going to be chirping 3,000 times in a minute. We can't always use our regression equation to predict everything. It's a good predictor if we've established that the linear correlation exists. It's a good predictor near the values that it was built around. It's not a good predictor outside of that. Okay, you have to be careful about extrapolating beyond those values. A little bit on either side is fine, but just not way on either side. So before we look at our next example, I want to talk about one thing. So is the regression equation a good model? So if it is a good model, and then what we can say is that we can substitute into the regression equation. And we know that because we've established that a linear correlation exists. The R indicates that a linear correlation exists. The p-value supported that. So if we've gone through and established all those things with the graph, the R, and the p-value, then yes, the regression equation is a good model so long as our data values are pretty close to what, as long as we're substituting in a value that's pretty close to what our data values were. If we don't establish that it's a good linear, that it's a linear correlation, that our R and our p-value support that, then if it's not a linear model, then our regression equation is not a good model to use to make a prediction. So what we have to do is we have to actually, instead of plugging into our model, we have to give y bar, which is the mean of the y values or the mean of the L2 values in our data set. So essentially, to kind of summarize this, if you have established that you have a linear correlation through the graph, the R, and the p-value, then you can use the regression equation as a predictor. If you have not established that, then the only prediction you can make is to give the average or the mean of your y's in your table. Okay, so looking at this one, again, if you feel comfortable approaching it, go ahead and try it and then check your answers. If not, stay with me as we go through this. So here we've got listed below are the ages of Oscar winners matched by the years in which the awards were won. Is there sufficient evidence to conclude that there is a linear correlation between the ages of best actresses and best actors? Okay, so first thing, construct a scatter plot. So we want to enter these for L1 and L2. And when we do that, we get a graph that looks like this. So already our graph does not look very linear in nature. The points are very spread out. If we do our, if we find our linear correlation coefficient by going to the Lin-Reg t-test and go down, then we see an R value that is pretty close to 0. So that's another indication it's probably not linearly correlated. And then if we look at the p-value, here is the p-value. If I compare my p-value, which is 0.365, to the alpha, which we're typically using of 0.05, my p-value is larger, so I'm going to fail to reject the null hypothesis, which basically says that I have no correlation. Okay, no linear correlation. So I found the p-value. So my R was negative 0.288. My p-value was 0.365. And we're going to say that there is no correlation between the two values, no linear correlation between the two values. Okay, so as far as the regression equation, your Lin-Reg t-test is still going to give you the A and the B, so you can still write your equation here. My A is going to be 51.61, and my B is negative 0.165x. We can actually take this plus out and just put a minus sign here. So this would be my regression equation. But because we were not able to establish a linear correlation, that a linear correlation existed, then we can't use this to make a prediction with. What we're going to have to do when we do this part F, find the best predicted age given that the age of the best actress is 54 years. We'll actually have to go back to my data set and average these Ys. So you could either add them all up and divide it out to get the average, or since you still have them in your calculator, what you can do that's a little bit quicker is to do the one variable stats for L2, since that's the Ys, and then here's that value. So my prediction for this is going to be 45 years. Okay. So we can only use our regression equation as a predictor if we have established that a linear correlation exists. Okay, so one other thing, R squared is actually important too, and that is going to be the proportion of the variation in Y that's explained by the linear relationship between X and Y. So if we square our R, that tells us what proportion of Y is explained by X. So like in the example there, if we have an R that's 0.801, then if we square that, we get 0.642. And so what we can conclude is that about 64% of the variation can be explained by the relationship that we have here. So that leaves about 36% that is not going to be able to explain by that. Okay, and one last thing here is that always remember correlation does not imply causality. We talked about this earlier in the semester, but definitely just because you show that two things are correlated, that does not mean that one causes the other. And like in this example that we were kind of looking at here at the very end quickly, it was looking at the relationship between eating chocolate and winning a Nobel Prize. Obviously, there's not a cause-effect relationship there, but there does tend to possibly be a causation, a slight correlation between the two. So you can have correlation without it being cause-effect. We also looked at an example early on where we talked about like ice cream sales going up as ski rentals go down. So there was a correlation between the two, but obviously one was not causing the other to happen. So you just have to remember that um, you can't always jump to the assumption that one causes the other. So some common errors that you might encounter are assuming that correlation implies causality, like we just talked about, using data based on averages and ignoring the possibility of a nonlinear relationship. So the third one there, like all these are not going to, what we learn in this section is not going to apply if it's some other type of nonlinear relationship that exists. So that's going to conclude chapter 10, and it's going to conclude all the new material that we're going to be encountering in this course. So from here on out, we're just reviewing for tests, reviewing for our exam, and getting ready for that. That does not mean to quit working. It just means that we are not going to be adding more information to what you're responsible for. So attend the Zoom sessions that'll be coming up, do the study guides, and hopefully you can finish strong. And I've enjoyed the time here studying statistics with you this semester, and I hope to keep in touch going forward.